Did you know that your old air conditioner could poison the soil, wreck the ozone layer, and even cost you thousands of dollars in fines? Every single year, Americans throw out millions of air conditioners, and each one is a ticking time bomb of toxic chemicals, heavy metals, and dangerous gases. In this video, I'm going to show you how they actually get recycled. Freon, copper, mercury, nothing gets spared. And trust me, this affects all of us. So first things first, why should anyone bother recycling an air conditioner the right way? To answer that, let's break down what's actually inside one of these machines. Air conditioners contain refrigerants. These are chemicals that can do serious damage to the atmosphere. Older units use ones that destroy the ozone layer. Newer ones, they may not harm the ozone, but they still contribute to global warming. The internal boards and compressors are loaded with toxic stuff like lead, mercury, and cadmium. If you just dump an old AC in a landfill, all that junk can leak out into the ground and water. Now, compressors also contain valuable metals like copper, aluminum, and steel. Those can be reused, cutting down the need to mine more raw materials. But here's the kicker. If you try to tear one of these apart without the right safety measures, those toxic materials can leak out, fast. That's why so many countries, including the United States, have strict environmental laws banning improper disposal. And yeah, in some cases, those fines are no joke. In the United States, old air conditioner disposal is regulated on a federal level by the Environmental Protection Agency, plus individual state rules on top of that. Now, we've already touched on how long these machines usually last. So let's dive deeper. Window and portable units typically last from 8 to 10 years. Split systems? They give you a few more. And those big centralized setups, yeah, the ones we mentioned earlier, they'll run for about 15 to 20 years. Keeping filters clean, topping off refrigerants, and doing regular checkups can stretch that lifespan. But in hot areas where ACs run all summer long, they tend to wear out faster. Once your system hits the end of its life, it loses efficiency. Your power bill goes up and repairs become a money pit. That's why most people end up replacing them, which means more units headed for recycling. There are several ways to recycle air conditioners in the US. A bunch of utility companies run take-back programs for old ACs. Some even offer cash, anywhere from $25 to $100, just for handing your unit over. All you gotta do is apply, and a technician comes out to pick it up and handle it properly. Big chains like Best Buy, Home Depot, and Lowe's will take your old AC for recycling too. Some states have dedicated drop-off sites for electronic waste where you can bring in your unit for free or a small fee. In many cities, there are special bulky item collection days. And some towns offer curbside pickup of old appliances, sometimes even for free if you book ahead. Even charities like Habitat for Humanity Restore take working ACs to resell or use in community programs. And a lot of stores have trade-in deals, where you bring your old one in and get a discount on a new model. When we're talking about centralized systems though, you can't just yank one out yourself. You need to call a licensed tech. They'll recover the leftover refrigerant using special equipment, then ship the whole system off for proper disposal. In many states, improper disposal can mean fines, from $100 to $500 on average. But in some cases, it can climb into the thousands. Bottom line, either take your unit to a recycling facility or use one of those special programs. That's the smart move. Once the AC arrives at the facility, the first step is a professional teardown to safely remove hazardous materials and prep everything for recycling. Removing Freon is a whole process that needs special tools designed to safely extract it from the system. The technician hooks up a refrigerant recovery machine to the AC's tubing system. This device uses vacuum pumps and pressure gauges to control the flow. The system gets opened through service valves, giving access to the Freon lines. The vacuum pump slowly pulls the refrigerant out and transfers it into a sealed recovery cylinder. The tech keeps an eye on the gauges to monitor pressure and make sure every last drop is extracted. Depending on the unit size and how much refrigerant is inside, this process can take anywhere from a few minutes to half an hour. During this step, the workers are fully suited up because contact with refrigerants can be harmful. The equipment's built to prevent any leaks. Everything happens in a sealed environment. Once the Freon is removed, it's stored in that sealed tank and later handed off to certified hazardous waste recyclers. With the refrigerant safely gone, the unit moves on to the disassembly phase, which is crucial for proper recycling. The techs set up special workstations at the facility. Before disassembly starts, they review the paperwork and lay out a plan, so they know exactly which parts to pull and how to sort them. The AC gets broken down into its core parts: the outer casing, compressor, heat exchanger, fan, electronics, piping, and smaller components. A typical unit has around 20 to 30 different pieces. The compressor alone might weigh between 30 and 50 pounds. Radiators, anywhere from 20 to 40 pounds each. They use both hand tools and machines, like hydraulic lifts and electric grinders, to cut or unbolt the big metal parts. This step takes about 30 minutes to 2 hours per unit, depending on size and complexity. Once everything's apart, the pieces are sorted by material: metal, plastic, and electronics. Around 90% of the metal in an old AC can be recycled. Metal gets cleaned of paint and grease, then sent for smelting and reuse. Plastics go to specialized recycling plants. Electronics that contain dangerous stuff, like lead and cadmium, are sent to e-waste recycling centers. On average, just one unit can provide 5 to 15 pounds of recyclable metal. That's a big deal when it comes to saving raw resources. Many recycling centers handle tens of thousands of air conditioners every year. That keeps a massive amount of toxic waste out of landfills. After the unit's fully disassembled, the next key step is sorting and prepping the materials for reuse. This process helps maximize resource recovery and shrink the environmental impact. After the initial cleaning, materials are sorted by quality standards. Metals get split into categories: aluminum alloys, steel, and copper. For example, copper wiring is often separated because its market value sits around $4 to $5 per pound. Plastic waste is grouped by type. The bundles for recycling usually weigh between 5 and 20 pounds. Electronic components are sorted by type: motherboards, capacitors, batteries. So recyclers know which ones need special handling, especially those containing rare metals. After sorting, all materials are packed up for transport. Metal parts go into containers headed for smelters. A single container can hold anywhere from 500 to 1,000 pounds of metal. Plastic granules are bagged or boxed up, usually in 50 to 100 pound batches, ideal for manufacturing. Electronics are shipped to specialized facilities, where they get broken down even further. Thanks to this whole process, a single air conditioner can yield a surprising amount of reusable material. Recycling and disposing of A to C the right way also saves energy. Smelting recycled metal takes about 60% less energy than making new metal from raw ore. And today, some companies are already rolling out tech to automate disassembly and sorting, making the whole system more efficient and less dependent on human labor. Have you ever seen a ship that does not touch the water? Now, imagine that such a vessel not only exists, but can also carry tens of tons of cargo and accelerate up to 250 miles per hour. Meet the hovercraft landing craft, a unique combat vehicle that glides above water, land, sand, and even ice. Its engines are just like those in fighter jets, and its maneuverability lets it drift on waves. But how much does this technology cost? How do they build it? And why are even seagulls afraid of these machines? Let's find out. The idea of using an air cushion came from the British engineer Christopher Cockerell in the 1950s. He experimented with airflows using tin cans and a hairdryer, ultimately creating the concept of a vehicle that could glide over any surface. In 1959, the world's first real hovercraft was launched. Later, this technology found its way into military use, specifically in LCAC-type landing crafts developed in the United States during the 1970s. So, Cockerell invented it, but the military refined the idea into its modern form. Let's move forward. Or maybe sail ahead. Manufacturing hovercraft landing crafts involves several stages. Initially, design bureaus create drawings and digital models of the craft. The design process depends on whether it's a new project or an upgrade of an existing one. Creating a completely new hovercraft takes from 6 to 12 years. Imagine that. Preliminary design and concept stages last from 1 to 3 years. Developing drawings and digital models adds another 2 to 5 years. Building and testing the prototype takes an additional 3 to 5 years. Finally, we get a ready-to-use craft. If we're talking about upgrading an existing design, the process takes half the time. Analysis and adaptation of drawings take from half a year to 1 year. Updating digital models takes only 1 or 2 years. Building and testing the updated version takes 2 to 3 years. The newest American hovercraft, called the Ship-to-Shore Connector, replacing the LCAC, began development in the 2000s. The first test models were ready in 2012 and 2014, but full-scale production started only in the 2020s. The process is lengthy because these crafts must be reliable, fast, and suitable for challenging operational conditions. After drawings and digital models are developed, suppliers of materials and components are selected. The military announces tenders, where companies compete for contracts. Manufacturers must pass certification and prove their materials withstand extreme conditions. Some components are produced exclusively domestically for national security. Thus, the process is complex but critically important. If even one component fails, the entire mission can be jeopardized. The craft's frame is assembled at shipbuilding yards. These massive industrial complexes are usually located on coastlines or near large rivers. They cover areas from dozens to hundreds of acres, since multiple vessels must be built simultaneously, with space for storing materials and heavy equipment. There are huge covered or open areas where ship hulls are assembled. These areas can be from 500 to 1,500 feet long to accommodate large structures. In metalworking workshops, aluminum alloys for the LCAC hull are cut, welded, and shaped using robotic machines and laser cutting. Shipyards also include dry dock basins, enormous artificial pools, where finished crafts are tested before launching. Massive gantry cranes with lifting capacities from 100 to 1,100 tons move large sections of hovercrafts. Additionally, there are areas for installing gas turbine engines, radar, and navigation systems, as well as logistics yards, where incoming materials and components from suppliers are stored. One of the largest such shipyards in the United States has been building military vessels for more than 100 years. The frame assembly of a hovercraft landing craft is constructed mainly from aluminum alloys, using welding and assembly methods different from traditional shipbuilding. Aluminum sheets and profiles are supplied as ready-made blanks. Robotic machines cut out parts according to computer-generated drawings. Sections for the future frame are prepared in special workshops. The LCAC structure is not assembled entirely at once, but built from large modules. Each module, for example, the bow, stern, and side sections, is assembled separately. Rivets and aluminum welding ensure durability. The frame consists of a keel beam running the length of the craft and transverse ribs providing rigidity. Aluminum rivets and specialized adhesive mixtures are used to connect sections, reducing weight. Large modules are lifted by powerful cranes and connected precisely using laser positioning to avoid errors. At the brightly illuminated shipyard, a giant module of the future craft rises into the air. A heavy gantry crane, weighing hundreds of tons, slowly lifts the aluminum section, gleaming in the sun like the shell of a marine predator. Metal cables are stretched tight like strings, while workers in protective helmets and vests carefully monitor every movement. The enormous part floats mid-air, gently swaying in the breeze. A crane operator, sitting high above the yard, maneuvers this colossus with extreme precision. Engineers below signal instructions, guiding the module to its exact position. When the section slowly settles into place, there's a dull metallic thud. Thousands of pounds of aluminum collide with the frame. Immediately, fastening begins. Workers tighten bolts, welding machines ignite with bright blue flames, and sparks scatter from beneath electrodes. The air fills with the scent of hot metal as the craft gradually takes shape, becoming a formidable combat machine. Engineers inspect structural integrity and tightness. Attachment points for the hovercraft skirt are installed on the frame. This system must be completely airtight to maintain LCAC stability during movement. The completed frame undergoes load and vibration tests. After passing successfully, engines, propellers, and electronics are installed. Now begins one of the most critical stages. The shipyard hums with crane motors, gently transporting massive gas turbine engines, the heart of the future craft. Workers dressed in protective suits and masks precisely position them in compartments, where every millimeter counts. Simultaneously, technicians attach enormous propellers, blades made from robust composite materials, which will later propel air with thousands of horsepower. When blades rotate for the first time, air waves ripple through the air, causing fabric on work uniforms to tremble. Inside, engineers connect cables, sensors, and onboard computers, carefully inspecting every chip, screen, and controller, as navigation, communication, and automated control depend on these systems. Once everything is ready, the moment of truth arrives. Pressing the first launch button, the massive frame shudders, turbines roar to life, and the first stream of hot air bursts from exhaust channels. The LCAC is ready for its first water test. A single modern LCAC costs from $50 to $75 million, depending on modifications. Operating costs are high due to gas turbine engines and demanding maintenance. Maintenance can occur at shipyards or specialized bases. Gas turbine engines require frequent service due to limited lifespans and costly repairs. The hovercraft skirt wears from contact with water, sand, and stones. Propellers and air systems require repairs as they operate continuously at high speeds. The United States is the leading producer of the new ship-to-shore connector crafts, replacing older LCACs. Great Britain builds similar crafts for civilian and military markets. Who uses them, you might ask? The United States Navy is the largest operator, possessing about 70 LCACs and acquiring new models. Japan uses LCACs for defense and humanitarian missions. Potential customers include NATO countries and nations expanding amphibious forces, like India and South Korea. Currently, LCACs are being upgraded to SSC, quieter, faster, and more efficient crafts. Demand is rising due to threats in the Pacific region and the need for rapid troop transport. Additionally, LCACs can drift. With the air cushion, they lack typical friction with water or land, allowing them to slide sideways, sharply change direction, and even pivot almost in place, making them exceptionally agile but challenging to control. LCACs use the same gas turbine engines as military aircraft, specifically the General Electric LM-2500. Similar engines power F/A-18 Hornet fighters. Essentially, LCACs are aircraft that never leave the surface. Unlike conventional ships, they can move onto shore, cross sandy dunes, swamps, and even ice, providing advantages for landing troops in difficult locations. However, LCACs are among the loudest vessels in naval forces. Their noise can be heard hundreds of feet away, making them unsuitable for stealth missions. During operation, LCACs create powerful vortices, capable of literally blowing away seagulls and other marine birds, often making it impossible for them to remain airborne. Every day in the United States, folks toss out 27,000 microwave ovens. That's nearly 2.5 million a year. But what happens to them once they're kaput? You'll be shocked at how wild the recycling process gets. From tearing apart transformers packed with hazardous stuff to digging out gold from circuit boards, every step is a jaw-dropper. How do factories handle hundreds of tons of metal daily? Why do magnetrons need special treatment? And what's the deal with the plastic parts? Stick around to the end to uncover the secrets of e-waste recycling. Recycling microwave ovens in the United States of America is a tricky business, involving a bunch of steps, all geared toward cutting down environmental harm and squeezing every bit of reusable material out of them. It all kicks off with properly disposing of the oven according to local rules and laws. Tons of towns have special e-waste drop-off spots where people can hand over their old appliances. Plus, big retail chains and microwave makers often run take-back programs, sometimes even tossing in discounts on new buys as a sweet deal. Once the thing lands at a recycling center, the first move is breaking it down and sorting out the main parts. This happens at specialized e-waste recycling hubs or appliance recycling plants. These places are scattered across the United States, mostly clustered in industrial zones or near big cities where electronic junk piles up fast. Some are private outfits, while others roll under city-run recycling efforts. First off, workers figure out if the oven can be reused or if it's headed for a full teardown. If the microwave's in rough shape, it goes straight to the disassembly line. They start by yanking off the outer shell, usually made of steel or aluminum. Breaking down microwave ovens can happen by hand or with machines. In smaller recycling spots, most of the work's done manually with basic tools like electric screwdrivers, pliers, hydraulic shears, and teardown stations. They unscrew the outer metal panels first, popping open access to the guts inside. Workers pull out the big pieces, like the magnetron, transformer, circuit boards, and wiring. The metal bits get squashed and shipped off to steel mills, where they're melted down for reuse. Inside every microwave is a magnetron, the thing that pumps out those microwaves. It's got ceramic insulators, copper coils, and a tiny bit of toxic stuff, like beryllium. Since beryllium dust can be nasty, magnetrons get handled with care, using protective gear and special recycling tricks. At big industrial recycling centers, they roll out automated teardown lines. A key player here is the electronic shredder. Think machines like the hammer mill or SSI dual shear, stretching 15 to 20 feet long and chewing through hundreds of microwaves an hour. After shredding, the materials hit magnetic separators, which pull steel apart from the rest. At heavy-duty plants, teardown's a multi-step gig with fancy machines. For transformers, they use hydraulic cracking presses to bust open the casing and get at the copper or aluminum windings. To snag precious metals from circuit boards, they dunk them in chemical baths or fire them up in furnaces at over 2,000 degrees Fahrenheit to melt out the good stuff. On average, big plants can rip apart 500 to 1,000 microwave ovens a day, depending on how much gear comes in and how automated they are. At smaller outfits, where it's mostly handwork, they process 50 to 200 units daily. Next, they yank out the circuit boards, loaded with resistors, capacitors, and microchips. These get handed off to companies that extract precious metals like gold, silver, and palladium. The copper wiring inside gets peeled out and recycled too. While exact numbers on precious metals from microwaves in the United States are hard to pin down, e-waste recycling overall brings a hefty haul of valuable materials back into the game. Another big piece is the high-voltage transformer, made of a metal core and copper or aluminum windings. Since it's got insulation that could be risky, recycling it takes some extra steps. The main hassle with transformers is their density and toughness, making it a chore to pull out the materials fast. Teardown starts by prying the transformer loose from the microwave's shell. This happens manually or with electric screwdrivers and teardown stations. Then it's hauled to the recycling zone. If it's by hand, workers use hydraulic shears, grinders, or metal cutting presses to slice open the outer casing. The transformer's core, usually layered steel, needs serious muscle to split, so big plants lean on industrial shredders or hydraulic presses. One slick way to crack transformers is with special crushing presses that smash the casing, letting workers fish out the insides. After that, the copper or aluminum windings get peeled off the core and sent for melting. Magnetic separators sort out the steel from the rest. Shredded bits ride a conveyor belt, and as they pass under a magnet, ferromagnetic stuff, like steel plates and transformer cores, sticks to it, then drops into a separate bin. Another type, the drum magnetic separator, uses a spinning magnetic drum. Shredded materials roll onto it, and magnetic force grabs the iron bits, spinning them along until they fall off into their own container once they're out of the magnetic zone. Beyond the mechanical approach, some plants use heat to break down insulation. Transformers get roasted in special furnaces at 1,000 to 2,000 degrees Fahrenheit to burn off organic junk and free up the metals. In some cases, they go with chemical leaching, soaking the transformer in acid, or alkaline baths to dissolve certain parts. Extra caution's needed with the insulation, since it might hold toxic stuff. Older models, for instance, used varnishes with polychlorinated biphenyls, nasty chemicals. So recycling those means wearing protective gear and sending the waste to special hazardous material plants. One slick way to crack transformers is with special crushing presses that smash the casing, letting workers fish out the insides. After that, the copper or aluminum windings get peeled off the core and sent for melting. Magnetic separators sort out the steel from the rest. Shredded bits ride a conveyor belt, and as they pass under a magnet, ferromagnetic stuff, like steel plates and transformer cores, sticks to it, then drops into a separate bin. Another type, the drum magnetic separator, uses a spinning magnetic drum. Shredded materials roll onto it, and magnetic force grabs the iron bits, spinning them along until they fall off into their own container once they're out of the magnetic zone. According to the United States Environmental Protection Agency, about 25% of e-waste, including microwave ovens, gets recycled. Every day, around 27,000 microwaves get retired across the United States, adding up to roughly 2.5 million a year. Recycling cuts down on landfill clutter, helping keep soil and water free of toxic leaks from electronic gear. Properly handling hazardous parts, like capacitors or insulation, stops harmful stuff from hitting the environment, which is a win for people's health and ecosystems. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves, and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns. Oil leaks, gasoline spills, lead contamination. Gasoline still contained lead back then. And other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Imagine this. By 2030, the entire world could be threatened by over 12 million short tons of spent lithium-ion batteries. But what actually happens to electric vehicles once they reach the end of their service life? It is not just simple disassembly. It is a high-technology process where even the remaining battery charge is used to power industrial facilities. Meanwhile, steel, aluminum, and plastic go right back into manufacturing, giving a new life to old automobiles. Watch until the end. You will be surprised by how efficient this recycling has become. The cost of electricity for charging is significantly lower than the cost of gasoline or diesel fuel, and the motor runs rather quietly. This, of course, increases the comfort of the ride. The most popular models are produced by Tesla, but there are many other manufacturers on the market, including Nissan, BMW, Audi, Mercedes-Benz, Volkswagen, Porsche, Rivian, Ford, General Motors, and Hyundai, which is quite a lot. However, even an electric vehicle eventually reaches the end of its service life. When the vehicle arrives at this end, it is sent for recycling. First, the car is deregistered, and then it is taken to special facilities that handle disassembly and recycling of vehicles. These can be recycling centers, auto dismantling sites, or recycling factories. Vehicles may be delivered by the owners themselves, or by dedicated services that pick up damaged or non-operational cars. Some facilities work with insurance companies or government organizations that coordinate disposal programs. When the car arrives at the site, it is initially inspected to determine which parts can be reused and which must undergo complete disposal. The site is typically an area equipped with bays or specialized zones where all processes take place. Mechanics and equipment operators work here, removing vehicle components both manually and with the help of machines. First, all technical fluids are drained. The car is placed on a special lift or in a separate drainage area. Operators use pumps or remove drain plugs to extract motor oil, transmission fluid, antifreeze, brake fluid, and fuel. The fuel is pumped out with vacuum systems to prevent fire hazards, and the motor oil is collected in containers for later recycling. After that, the disassembly of the vehicle begins. The battery is removed first and sent to a separate recycling process. There, it is tested to determine the level of remaining charge and suitability for reuse. The removal must be done carefully, as the battery contains toxic and flammable materials. This can take from 30 minutes to 60 minutes by itself. If the battery can still hold a charge, it is used in stationary energy systems, for example, to store energy from solar panels. If the battery is completely worn out, it is sent for disposal. To monitor battery condition even before disposal, Tesla, for instance, uses its own software that can remotely evaluate the remaining capacity, the level of cell degradation, and the overall condition of the vehicle's energy system. This makes it possible to determine whether the battery can be used in secondary energy applications or must be fully disassembled. Through this approach, the company reduces the number of batteries immediately sent for disposal, extending their life cycle as stationary energy storage systems for as long as possible. The recycling of Tesla electric vehicles happens in much the same way as the recycling of other electric vehicles, but there are certain specifics due to the battery design, the body materials, and the software. Tesla batteries have a complex modular structure and a high energy density, requiring additional safety measures, including a complete discharge and controlled disassembly. A full discharge of a Tesla battery is carried out at specialized recycling centers, where strict safety measures are followed to avoid the risk of fire or explosion. This is done using special equipment that gradually removes any leftover electrical energy, placing the battery into a safe state. Because lithium-ion batteries maintain a high energy density, they can still hold a substantial charge even after extended use, making the discharge process critically important prior to further recycling. According to estimates, by the end of 2030, around 12 million short tons of spent lithium-ion batteries could end up in landfills if effective recycling systems are not put in place. To discharge the battery, industrial systems of controlled power consumption are connected, gradually drawing off the remaining energy. These machines operate on the principle of creating a controlled electrical load, simulating energy consumption, where electrical energy is converted into heat that is then dissipated by active cooling systems. Another method involves connecting the battery to industrial energy storage systems, which can use the residual charge to power facilities or feed electricity back into the grid. The process occurs in a controlled environment with low humidity to minimize the risk of corrosion and unwanted chemical reactions. The temperature is maintained between 50 degrees Fahrenheit and 68 degrees Fahrenheit because higher temperatures can accelerate degradation of battery cells, while lower temperatures increase the risk of electrolyte instability. The operator oversees discharge parameters through computerized monitoring systems, which record voltage, current, and battery temperature in real time. Once the charge falls to a safe level, typically below 1% of the original capacity, the battery is considered discharged and ready for further disassembly. The battery is taken apart, separating the casing, modules, and electronics. Each module consists of thousands of lithium-ion cells that must be properly recycled to recover valuable metals. The modules are mechanically shredded in specialized installations that operate in an inert gas environment or under liquid nitrogen to prevent spontaneous combustion of any leftover active materials. The resulting shredded mass undergoes either thermal treatment or chemical solutions to remove organic components such as electrolyte and binding substances. After processing, the recovered metals are reused in the production of new batteries, and the remaining materials are disposed of in accordance with environmental standards. Toxic waste is neutralized at specialized facilities. Currently, only about 5% of lithium-ion batteries are recycled worldwide, indicating a major opportunity to improve recycling infrastructure. One key method for recovering valuable materials is hydrometallurgy. This process involves dissolving shredded elements in specialized chemical solutions that allow for the separate extraction of nickel, cobalt, lithium, and other metals. Compared to the traditional pyrometallurgical method, which uses melting at high temperatures, hydrometallurgy is more energy efficient and environmentally safe because it allows the extraction of pure metals without significant air emissions. Thus, the batteries are disassembled, casings and electronic components are recovered, and then the active electrode material is shredded. The resulting shredded mass is referred to as black powder, as it contains oxides and other metal compounds. Next, this powder is dissolved in an acidic environment using, for instance, sulfuric or hydrochloric acid. This stage is known as acid leaching, during which the metals convert into a solution. As a result, a liquid mixture forms that contains ions of lithium, nickel, cobalt, and other elements. The next step is extraction and selective precipitation. Using reagents such as organic extractants or precipitating agents, specific metals are extracted from the solution. For example, lithium may be precipitated as lithium carbonate or lithium hydroxide, both of which are used in the production of new batteries. Nickel and cobalt can be extracted by altering the alkaline solution or by precipitation using sulfides and hydroxides. After precipitation, the metals undergo additional purification, including filtration and recrystallization. The end products, metal salts or metal oxides, are sent back into production for new battery cathode materials. The efficiency of hydrometallurgy makes it possible to recover over 90% of nickel, cobalt, and manganese, as well as up to 90% of lithium. This significantly reduces the need to mine new resources and promotes a closed-loop battery manufacturing cycle. After disassembling and processing the batteries, the electric vehicle recycling process continues. The motor and transmission are removed if they are suitable for reuse or repair. This can be done by people manually, using wrenches, jacks, and other tools, or by robotic systems that simplify the process. Wheels, radiators, electronics, and glass are also removed, and these components can be sold separately or recycled. Window glass, for instance, is recycled by shredding it into granules, which are then used in construction or to produce new automotive glass. Plastic components, such as bumpers, interior panels, and fuel tanks, are processed by shredding and later used to create new products. Only when all valuable and hazardous components have been removed from the car do they proceed to recycle the body. It may be cut into large pieces using hydraulic shears or sent directly to a shredder. Shredders reduce the metal frame to small fragments, which are then sorted by material type. Steel and aluminum are separated using magnets or electronic sensors, after which they are sent for remelting. Those parts of the vehicle that cannot be recycled may be disposed of by incineration to produce heat energy, or buried at specialized landfills. The entire process can take anywhere from a few hours to several days, depending on the type of vehicle and the level of automation at the facility. However, with modern technology, the percentage of materials that can be reused is constantly rising, and it currently exceeds 3/4 of a vehicle's total mass. Imagine this. Every single year, all around the world, over 70 million automobiles are manufactured, and each one of them demands high-technology glass. From the broken flask with nitrocellulose that accidentally revealed laminated glass, to the powerful hydrophobic coatings, the history of this material is truly astonishing. Today, we are going to learn how glass becomes ultra-strong, safe, and prepared to protect us from wind, rain, and the dangers of the road. Please get ready for a journey into the realm of advanced modern technology. Thousands of short tons of glass scrap are recycled in order to create crystal clear windows for automobiles. It is not only about safety, but also about saving precious resources. And that is just the beginning. The history of automobile glass production is closely linked to the development of the automobile industry, which emerged in the late 19th century. The glass used in today's automobiles has undergone a long path of improvements that have made it safer, stronger, and more functional. When the very first automobiles began to appear, they were initially not equipped with any glass at all. The open body design offered only partial protection to passengers, while dust, wind, insects, and other hazards made traveling extremely uncomfortable. Later on, when automobiles became faster, the need for driver and passenger protection emerged. Windshields were first made from ordinary window glass, which, although it provided some degree of protection, had a serious drawback. In accidents, it would shatter into large, sharp fragments that resulted in numerous injuries. The first groundbreaking discovery in the field of automobile glass was the creation of laminated glass. This happened by chance. In 1903, a French chemist named Edouard Benedictus accidentally dropped a flask coated with nitrocellulose. The glass cracked but stayed in one piece, thanks to the thin layer of plastic. This accident inspired the scientists to develop a multi-layered glass, which later became the basis for triplex. By the 1910s, laminated glass was already being used in premium class automobiles. Its construction consisted of 2 layers of glass with a thin, transparent film in between them. In the event of impact, the glass did not scatter, and cracks remained on the film. In the 1920s, laminated glass began to be widely used in the production of windshields. Its main advantage was increased safety. Even in serious accidents, the fragments did not fly apart, but remained embedded in the polymer layer. The next stage in the evolution of automobile glass arrived in the 1930s, when the technology for making tempered glass was patented. This material was produced by heating the glass to high temperatures followed by a rapid cooling. As a result of such a process, the glass became stronger, and upon breaking, it would fracture into small pieces with dull edges, minimizing injuries. By the middle of the 20th century, tempered glass was being used for the side and rear windows of automobiles. It was less expensive to manufacture compared to triplex, and provided a sufficient level of safety for those parts of the vehicle. In the 1950s and 1960s, automobile glass became even more advanced thanks to ongoing technological progress. During this time, several important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and more durable. Mass production. The automation of manufacturing processes drove down the cost of automobile glass, making it more affordable for a wide range of consumers. Coatings for sun protection. Special coatings that blocked ultraviolet rays and reduced the heating of the automobile cabin were used for the first time. One of the most significant technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, enabled the manufacturing of perfectly smooth glass by allowing molten glass to spread across the surface of molten tin. Through this method, the glass became more uniform, stronger, and better suited to mass production. Even today, the float method remains the foundation of automobile glass manufacturing, ensuring precise dimensions, a smooth surface, and high quality. In the second half of the 20th century, automobile glass underwent even more changes aimed at improving both safety and comfort. In the 1960s, heating filaments began to be installed in the rear window of automobiles, preventing condensation and freezing. In the 1980s, glass was introduced with special metallic coatings that reflected sunlight and reduced heat buildup inside the vehicle. Glass with ultraviolet protection. With the introduction of new technologies, automobile glass began providing virtually complete protection from harmful ultraviolet radiation. And now, we enter the modern period of automobile glass production, which we will discuss at this very moment. We shall start with the glass used in automobiles. Automobile glass is divided into several types, depending on its purpose and manufacturing technology. Windshield. This is usually multi-layered glass composed of 2 sheets of glass with a polymer film between them. This design ensures that, if damaged, the glass does not break into sharp fragments. Side and rear glass. Most often, this is tempered glass, which, upon impact, fractures into small, blunt-edged pieces that reduce the risk of injury. Panoramic roofs, or other special types of glass, often use laminated or tempered glass with specialized coatings for protection against ultraviolet radiation. The main components of glass are natural materials, which are mixed in certain proportions to achieve the desired properties. Quartz sand is the principal element in glass, giving it transparency. It must be extremely pure and contain minimal impurities. Soda is added to lower the melting temperature of glass. Lime improves the mechanical durability and chemical characteristics of glass. Additional additives. These are used to adjust color, transparency, resistance to ultraviolet light, and other properties. The raw materials are cleaned, dried, and ground to a uniform state. It is crucial to eliminate as many impurities as possible, as they can affect the quality of the glass. After preparation, the raw mixture is poured into special furnaces for melting. This stage includes a few important steps, so let us review them together. Melting temperature. To create molten glass, a temperature of about 2,732 degrees Fahrenheit is used. Throughout the melting process, the raw materials transform into a uniform, viscous liquid. Homogenization. The molten glass is stirred to distribute components evenly. This is important for preventing air bubbles or other irregularities in the finished product. The furnaces for melting glass are equipped with modern systems for temperature control and process automation, which guarantee the high quality of the final product. After melting, the molten glass proceeds to the forming stage, most commonly performed using the float method in modern manufacturing. Feeding the molten glass. The liquid glass flows from the furnace onto a bath of molten tin. Due to the high density of tin, the molten glass spreads out uniformly across its surface. Under its own weight, the glass forms a perfectly even and smooth surface. Gradually lowering the temperature makes the glass grow solid. By the time it leaves the tin bath, it is ready for further processing. The float method allows the production of glass sheets with precise geometric parameters and a very high quality finish. Once it is cooled, the sheets of glass are cut to the sizes required for automobile manufacturing. Automated cutting machines ensure accuracy, and to prevent chips or cracks, the edges of the glass are polished. Every sheet is checked for defects, such as micro cracks, bubbles, or other damage. Next, to ensure the strength and safety of automobile glass, it undergoes the process of tempering. The glass is heated to a temperature of around 1,112 degrees Fahrenheit. Then the surface is quickly cooled by air jets, while the inner layers cool more slowly. As a result, stress is created, which greatly increases impact resistance. Tempered glass, when broken, shatters into small, safer fragments, minimizing the risk of injuries. After that, for the windshield, a triplex construction is used, which is a combination of glass and polymer film. Its fabrication involves several steps. Layer bonding. A polymer film is placed between two sheets of glass. The construction is placed into a vacuum press to remove air bubbles. Then the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure, ensuring a strong bond between the layers. Triplex has high impact resistance, and if damaged, the fragments stay attached to the polymer film, thus providing safety for the driver and passengers. Afterward, to enhance the properties of automobile glass, various coatings are applied. Anti-glare coatings reduce glare from the sun or from other vehicles' headlights. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings allow water to bead and roll off the glass surface. Heating elements. Thin heating filaments can be embedded in the windshield, making it easier to remove ice or condensation. To achieve the required shape, special thermoforming equipment is employed. The glass is heated to a temperature at which it becomes pliable, and it is then molded according to specified parameters. And here we arrive at the final stage. During this stage, each piece undergoes a thorough inspection. The transparency is tested, and any defects are identified. Next, the glass is tested for impact resistance and durability under load, compliance with standards, the accuracy of dimensions, the shape, and other parameters are verified. Then the finished automobile glass is packaged in a manner that prevents damage during transportation. It is delivered to automobile factories or service centers, where it is installed in vehicles. The production of automobile glass is a high-technology process that brings together physics, chemistry, and engineering. Thanks to advanced technologies and strict quality control standards, automobile glass ensures safety, comfort, and longevity. And just imagine how many stages automobile glass must go through so that we can watch over road safety and admire wonderful vistas along the way. I find it remarkable. Do you also think so? Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP1, developed in the year 1944, was an early standard for military aviation. JP4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP8, replacing JP4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed negative 52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.46 two-thousandths of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think? This is one of the most expensive and complex machines ever built by humankind. Constructing it costs more than $3 billion and takes over 7 years to complete. It can dive to depths of more than 3,000 feet, remain submerged for months without surfacing, and launch missiles capable of altering the course of war. But how exactly is a nuclear submarine, an engineering masterpiece that remains nearly invisible even to the most advanced radars, built? Right now, you are about to witness this incredible process. A nuclear submarine is a highly sophisticated engineering marvel, and its creation begins long before the first sheet of metal ever touches the manufacturing tools. The initial designs are developed using advanced computer modeling software. At this stage, several critical parameters are considered, including hull dimensions and shape, power systems, weaponry, and noise reduction technologies. The length can range from 300 to 550 feet, directly impacting the submarine's diving depth based on its class. The most advanced submarines can descend to depths of 2,000 or even 2,500 feet, while some experimental models can go beyond 3,000 feet. Based on these initial designs, physical models of the submarine are constructed and tested in water tunnels. This allows engineers to analyze how the hull shape affects maneuverability, water resistance, and noise levels. Meanwhile, computer simulations help predict the submarine's behavior underwater at different speeds and during various maneuvers. Once all simulations confirm the calculations, the blueprints are sent to production. This is where theory turns into practice. Building nuclear submarines requires special materials capable of withstanding extreme pressure at great depths while providing corrosion resistance. Typically, high-grade steel or titanium alloys are used. Steel is more cost-effective and easier to manufacture, as it can endure high pressure and impacts. Titanium, on the other hand, offers superior strength, corrosion resistance, and non-magnetic properties, which reduce the risk of detection. However, titanium is more challenging to process and weld, as its melting point is significantly higher, approximately 3,034 degrees Fahrenheit compared to steel's 2,500 degrees Fahrenheit. Before construction begins, all metal sheets undergo heat treatment, which involves heating, cooling, and applying special anti-corrosion coatings. The hull of a modern submarine is assembled from modular sections, simplifying the construction process. Metal sheets are cut with massive laser and plasma cutters, ensuring precision down to the millimeter. Each sheet is then shaped using hydraulic presses to achieve the desired curvature. Some parts of the hull feature spherical or cylindrical structures. The sections are assembled separately. These are massive rings, or compartments, that will be joined in the final stage. This modular approach allows different sections of the submarine to be worked on simultaneously, accelerating the overall construction timeline. Once all components are ready, the most critical phase begins: welding the hull. Welded seams must be exceptionally strong, as even a microscopic crack could lead to catastrophe at great depths. To meet all safety standards, automated electron beam welding is used, producing perfectly uniform seams. Additionally, every weld is inspected using ultrasonic scanners and X-rays. Most nuclear submarines feature a double hull design. The strong inner hull withstands deep sea pressure, while the outer hull provides a streamlined shape, improving hydrodynamics and reducing detectability. Ballast tanks are often located between these hulls, allowing for buoyancy control. To keep the submarine as stealthy as possible, anti-sonar coatings are applied. These include noise-dampening polymer tiles that absorb sound waves, microporous composite materials that minimize the submarine's acoustic signature, and noise-reducing coatings for the propellers and power systems. Once all sections are ready, they are connected. Gigantic cranes transport the compartments into specialized docks, where they are bolted and welded together. The completed hull is then tested for air tightness by filling it with compressed air and checking for leaks. A structural integrity test is also conducted in a hydrostatic pressure chamber, simulating real deep-sea conditions. Once the submarine's hull is assembled and its strength verified, it is time to install its most crucial component, the nuclear reactor. This is the heart of the submarine, allowing it to stay submerged for months, or in some cases, even years. A nuclear reactor is more than just a machine. It is an entire energy system consisting of various auxiliary components that occupy a significant portion of the submarine. Modern nuclear submarines use reactors that function by heating water to generate steam. The nuclear fuel, typically enriched uranium-235 or uranium-238, is placed inside the reactor's core. As nuclear reactions occur, heat is produced, which then heats water in a closed-loop system. The resulting steam drives turbines that generate electricity and power the propeller. The reactor is transported in protective containers and installed using cranes through a designated hatch on the upper part of the hull. It is placed within a specialized compartment in the submarine's core, surrounded by radiation-blocking materials. This compartment is also equipped with emergency cooling systems and reinforced safety barriers. The reactor is mounted on a shock-absorbing platform that minimizes vibrations and impacts during submarine movement. Next, heat exchangers and steam generators are installed to ensure efficient coolant circulation, followed by the installation of turbines and electric generators, critical components for the submarine's overall operation. Finally, the compartment is sealed with multi-layered lead and composite panels to minimize radiation exposure to the crew. To ensure functionality, an initial test ignition of the reactor is performed. During this test, power levels are gradually increased, radiation levels in all compartments are measured, and cooling systems are tested under maximum loads. With the reactor in place, the submarine is still far from operational. At this point, it consists of empty corridors and compartments, so the next step involves installing control systems, life support mechanisms, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull, enabling the detection of enemy vessels and underwater terrain mapping. The onboard computer system and automated combat control stations are integrated, ensuring precise maneuvering capabilities. Weapon systems are also installed. Torpedo tubes are positioned at the front, equipped with automated reload mechanisms for rapid firing. Strategic submarines are fitted with missile launch silos located in the central hull. Each silo is equipped with hydraulic locks and pressure control systems, allowing for missile launches at extreme depths. Considering that the crew can remain submerged for months without surfacing, nuclear submarines must be self-sufficient. They are equipped with oxygen generators, carbon dioxide removal systems, heating and ventilation mechanisms, and water reserves. Ever seen those tiny capsule hotels? Well, submarines have something very similar: sleeping capsules. They also feature dining areas stocked with provisions and a command center filled with control panels, maps, and communication devices. After the living quarters are fully equipped, the submarine is almost ready for deployment. But the most thrilling phase remains: a series of rigorous tests to prove that it can withstand immense pressure, stay undetectable, maneuver in extreme conditions, and perform combat missions. These tests can last anywhere from 6 months to 2 years, and include both factory trials and combat training for the crew. The submarine undergoes another airtightness test, followed by assessments of its electrical and navigation systems, and a final reactor ignition. For the first time, the submarine leaves the shipyard and enters open waters. Stabilizers, hydraulic cylinders, and steering mechanisms are tested. Sharp turns, dives, emergency maneuvers, and maximum speed tests, typically 25 or 35 knots, are performed. The submarine then submerges to periscope depth, about 65 feet, to evaluate stability. At greater depths, ballast tanks are tested under load, and the submarine is gradually lowered to its maximum allowable depth, usually around 2,000 feet, depending on its class. Reactor performance under maximum load is also assessed. Once the submarine has proven its seaworthiness, combat systems are tested. Initial shots are fired using training torpedoes without warheads. Strategic submarines conduct the launch of a single ballistic missile, typically following a launch-dive airburst trajectory. Tactical submarines perform test launches of Tomahawk missiles or similar weapons. The submarine also enters an area with hydroacoustic sensors, where specialists measure noise levels at various speeds and evaluate the effectiveness of its sound-absorbing rubber coating. Finally, the submarine undergoes a simulated combat mission, during which the crew must demonstrate full operational readiness. What if I told you that every bottle you throw away could live an infinite number of lives? Ardagh Group creates more than 160 million packaging units each year, using thousands of tons of recycled glass. Now imagine the scale: industrial crushers that process up to 3 tons of glass per hour, and furnaces working at full capacity to give this material a new life. What does this grand transformation look like? Keep watching. You will be amazed. The company participates in various programs aimed at reducing landfill waste, actively collaborating with municipalities and other organizations to collect and recycle glass. Through these efforts, Ardagh increases the proportion of cullet used in production, as reusing glass is more energy efficient than making new glass from raw materials. For example, the company supports deposit packaging systems, where consumers return used glass bottles for recycling. They also work with waste sorting centers, providing equipment to clean and prepare cullet for processing. In many countries, Ardagh funds community education programs to raise awareness about the importance of recycling glass. Through these initiatives, Ardagh Group not only minimizes landfill waste, but also significantly reduces production energy costs, as glass made from cullet melts at lower temperatures. This is an essential part of their sustainability strategy, focused on conserving natural resources and reducing environmental impact. Each year, the company produces over 160 million packaging units, highlighting its scale and importance in the global market. Thanks to advanced technologies and high manufacturing standards, Ardagh Group remains an industry leader, contributing to economic development and environmental responsibility. The story of Ardagh Group began in 1932 in Dublin, Ireland, when the company started as a small glass packaging manufacturer. Its founders aimed to meet the growing demand for glass bottles, driven by the expanding food and beverage industries. In its early years, the company produced bottles for local breweries and dairy businesses, gradually increasing its scale. A pivotal moment came with the strategic decision to expand through acquisitions. In the 1990s, the company began acquiring plants specializing in glass containers across Europe and beyond. It later entered the metal packaging sector, diversifying its business and tapping into new markets. Today, Ardagh Group is a global leader in packaging production. Its growth story is one of transforming from a small regional manufacturer into a world-renowned corporation that remains committed to its mission, creating high-quality, sustainable packaging that meets the needs of the modern world. Ardagh Group embraced the use of recycled glass as part of its commitment to addressing contemporary environmental challenges and economic trends. Glass is an ideal material for reuse, as it can be recycled an infinite number of times without losing quality. Over time, the company realized that transitioning to more sustainable production practices was not only an ethical necessity, but also a powerful business strategy. Several factors influenced this decision. First, growing demand from customers seeking eco-friendly packaging. In a world where more people are concerned about climate change and pollution, glass containers made from recycled materials have become an attractive solution for many brands. Second, economic benefits. Using recycled glass reduces energy costs. Melting cullet requires 30% less energy than producing new glass. This, in turn, lowers carbon emissions. Thus, using recycled glass has become a key part of their business, supported by both environmental and economic advantages. Garbage trucks deliver collected glass to specialized recycling facilities. There, it is first inspected to sort out materials unsuitable for recycling, such as ceramics, plastic, or metal. Next, the glass is crushed into cullet, small pieces that are easier to melt and clean. This cullet is then transported to glass manufacturing plants, where it is used as raw material for producing new bottles, jars, or other glass containers. The glass arriving at the recycling plant is initially inspected and sorted. Automated systems or manual processes remove foreign materials, plastic, metal, paper, or ceramics, that could disrupt further processing. The company employs approximately 20,000 workers globally. Before crushing, the glass is washed. Powerful systems rinse away dirt, labels, and product residues. High-pressure water jets remove everything: dried ketchup, wine remnants, stuck-on labels, and even tiny bits of paper that seem impossible to clean off. This step is crucial for ensuring the purity of the raw material. Water streams splash everywhere as the glass passes through special brushes and rollers spinning at high speed, polishing each piece to a shine. The noise resembles a small waterfall storm. Watching clean, perfectly shiny glass emerge from the machines is a spectacle, transforming what was once dirty and labeled into something pristine. It feels like magic, but it is actually cutting-edge technology at its best. The cleaned glass moves into specialized crushers. There, it is ground into small particles using powerful mechanical hammers or rollers, resulting in fragments ranging from a few millimeters to several centimeters. This material, known as cullet, resembles gravel. Industrial hammer crushers can process up to 3 tons of material per hour. To remove any remaining foreign materials, the cullet passes through magnetic separators for metals and air jets for plastic and paper. Additionally, laser or optical scanners automatically sort the glass by color into clear, green, and amber categories. Sorting glass by color is not merely an aesthetic choice, but a critical technological process with several practical benefits. Colors affect the final quality and properties of the new product. For instance, clear glass is used for beverage or cosmetic bottles and must be kept as pure as possible. Green or amber glass, on the other hand, is ideal for packaging that protects contents from ultraviolet light, such as beer or wine. Color sorting is also essential for melting, as each glass type has unique temperature and chemical characteristics. Mixing colors can destabilize the process and risk producing defective batches. Mixed colors are harder to recycle. Such glass is often sent to lower priority uses or not reused at all, increasing waste. Properly sorted glass reduces energy consumption during recycling, as there is no need to clean the material of color impurities. Therefore, color sorting not only ensures the purity and quality of new glass, but also significantly reduces energy costs and maximizes the use of recycled resources. The finished cullet is stored in bins or bags and transported to glass manufacturing plants. Depending on the requirements, it is used as raw material for producing new glass. Though cullet appears sharp, storing it in bags is entirely feasible due to specialized materials. These bags, called big bags or flexible intermediate bulk container, are made of ultra-durable polypropylene with multiple layers that prevent tearing, even from sharp glass edges. Sometimes, the inner layer of big bags is additionally coated with laminated material for extra strength and dust resistance. The cullet, reduced to pieces ranging from a few millimeters to several centimeters, has edges that are less likely to puncture the bag material. Storing in such big bags is not only safe, but also highly convenient. The bags are easy to transport, stack, and dose for further use in furnaces. After preparation, the cullet is transported to RDOG Group factories, where it is transformed into new glass products. A significant portion of the cullet is loaded onto trucks, either standard or specialized, depending on the volume and route. For larger shipments, even rail cars are used to cut transport costs and reduce the carbon footprint. Upon arrival at the factory, the cullet undergoes another inspection. This ensures that the material meets all requirements, such as the absence of any foreign impurities or pieces of the wrong color. Afterward, it is fed into melting furnaces, advancing the recycling process to the next level. Incidentally, the closer recycling plants are to manufacturing facilities, the more economically and environmentally efficient the entire chain operates. This is another reason why RDOG Group actively supports local glass collection and recycling systems. Imagine a place where the trains of the future are born every single day, a place that brings together innovation, sustainability, and history. The Siemens Mobility Factory in Sacramento is over 2 million square feet of manufacturing space, creating the locomotives that move America. Here, one of the largest 3D printers in the world is installed, and up to 80% of the energy comes from solar panels. Curious about how trains are tested? They are run on specialized tracks to evaluate speed, noise, and stability. This is not just a factory, it is a true innovation lab. The story of this factory began back in 1984, when Siemens decided to invest in the future of rail transport in the United States. But they needed more than just technology. They needed a reliable base, and Sacramento was the perfect choice. What does the capital of California have to do with train manufacturing? Actually, the location choice was very strategic. Sacramento has a long history of railroad infrastructure. As far back as the 19th century, this city was one of the key hubs of the Transcontinental Railroad. In other words, the railway spirit has been alive here for over 150 years. Additionally, the region had access to a large number of skilled workers who could contribute to manufacturing. On top of that, the proximity to ports and other transportation hubs in California ensured smooth logistics. When the factory first opened, it was relatively small. Siemens Mobility was just beginning to build its brand in the United States. Initially, the factory specialized in manufacturing locomotives and trams. However, the company's ambitions were massive. They saw the need for modernizing American rail transport and decided to become part of this revolution. Within just a few years, the factory began scaling up production while implementing cutting-edge technologies. Over time, it started producing trains that you can now see in dozens of American cities. The Siemens Mobility factory continued to grow. In the 2000s, it began producing modern high-speed trains and electric trains that meet the highest standards of comfort and energy efficiency. One of the key milestones was the expansion of the manufacturing facilities. The factory grew to over 200,000 square meters. This allowed for increased production capacity, the addition of new car manufacturing lines, and even testing grounds. Today, the Siemens factory in Sacramento is one of the most sustainable manufacturing sites in the world. Approximately 80% of its energy comes from on-site solar panels. Water usage is maximized for efficiency, and nearly all material waste is recycled. By the way, this factory produces trains for Amtrak, Brightline, and various urban rail systems, including the Los Angeles Metro and Minneapolis streetcars. The factory emphasizes localization. About 90% of the materials used in train manufacturing are supplied by American companies. This not only reduces logistics costs, but also supports the local economy, enables quicker responses to market needs, and ensures that the products meet client requirements. Siemens Mobility does not stop innovating. They are already working on trains with hydrogen engines and autonomous driving systems. While specific statistics on these projects may be limited due to commercial confidentiality, it is known that the company invests significant resources in research and development in these areas. So, how are trains made? It all starts with large sheets of aluminum and steel, which are cut and formed into components for train cars. And you know what? I was amazed by how organized the process is. Even at the stage where you are just looking at pieces of metal, everything is planned down to the smallest detail. Assembling a single car can take weeks, and an entire train, months. But the result is worth it. When they arrive at the factory, they are immediately distributed into zones based on what will be made from them: walls, floors, roofs, or smaller components. This is not just a pile of metal. It is all sorted and labeled with special codes. This ensures that no piece gets lost and that production does not halt due to confusion. The metal is cut on specialized machines that use lasers or plasma cutting, and there is no room for error. Every piece is cut with millimeter precision. But here is the interesting part. There is almost no waste. Leftover pieces are reused to create smaller components or sent for recycling. This is not just cost saving, it is sustainable. The metal is used, for instance, to create train car exteriors. These are made of aluminum for a good reason. This material is both lightweight and strong, making it ideal for high-speed trains. I was even told that it is environmentally friendly. Aluminum can be recycled almost infinitely. Impressive, right? Cutting robots and hydraulic presses create parts that undergo further processing. Everything here is ultra-precise. There is no eyeballing it. In the next workshop, the train's frame is welded. Once the car bodies are ready, robots and highly skilled workers step in. I watched as each part was installed one by one, from roofs to floors, from walls to doors. It is like a massive Lego set, but on a scale you can hardly imagine. In this workshop, the car frame is born. Every weld is checked to ensure it can withstand future loads. Imagine sparks, bright lights, and sounds like in a blacksmith shop, but with robots. Workers install windows, doors, seats, electrical systems, ventilation, everything that makes a train comfortable for passengers. Next, the train is painted with weather-resistant paint. And yes, everything here is as eco-friendly as possible. Filters capture harmful substances to prevent environmental damage. But the most fascinating part starts with the details. Did you know that every train car interior is essentially a small universe? Wiring, control systems, air conditioning, seats, everything is installed with meticulous precision. One worker even joked, "Every single screw here is worth its weight in gold." Another thing that amazed me was how many processes are automated. For example, electronics inside the cars are tested using special simulators. It is like a video game where the system checks if all buttons, displays, and even Wi-Fi are working. Now picture this. Before a train hits the tracks, it is tested on a special track. Yes, they literally run it here to measure speed, stability, and even noise levels. Watching this giant accelerate is a whole new level of satisfaction. Here is what makes factories like Siemens Mobility special. Everything works in harmony. On one hand, there are people working with their hands, putting a piece of themselves into every car. On the other hand, there are robots and automated systems making the process faster and more precise. I was even shown one of the largest 3D printers in the world, which prints train parts. Imagine this. Instead of waiting for parts to be delivered from across the globe, the factory can make them right here, right now. It is not only convenient, but also eco-friendly. Less transportation means fewer emissions. For instance, the 3D printer produces mounting nodes, frame elements, and even special ventilation components. Traditionally, these would need to be cast or welded, but here everything is done more precisely, faster, and more efficiently. Fairings, structural components, interior details, spare parts, and prototype versions of parts can all be printed, saving materials and time. Okay, some might ask, what is so special about this? Trains are just trains. But no, each of these modern cars is a step forward in transportation development. More sustainable materials, energy-efficient systems, passenger comfort, all of this impacts not just us, but the future of our planet. Moreover, factories like the one in Sacramento create jobs and introduce new technologies that can later be applied in other industries. It is a place where technology and people come together to create something truly remarkable. Oh, you cannot even imagine how massive this factory is. The Siemens Mobility facility in Sacramento spans approximately 2 million square feet. Picture several football fields connected into one giant structure. It is a city within itself. Workshops, conveyors, rail tracks, repair shops, and even test tracks for finished trains. The factory is divided into several zones, each responsible for a specific stage of production. When I left the factory, I felt like I had visited the future. This is a place where innovation, craftsmanship, and human talent combine. If you ever get a chance to visit something like this, do not miss it. It is truly impressive and changes how you see the world. So, are you ready to hop on a train next time and think, how was this made? How do you build an engine that can handle temperatures over 3,200 degrees Fahrenheit and carry a Boeing jet across the ocean? Sounds like science fiction, right? But this is the reality of modern engineering. Imagine this. Every single part, from turbine blades to combustion chambers, is crafted with micrometer precision. Metals that don't melt under extreme heat and 3D printing that's changing the game. Dive into the process of creating the heart of an airplane, where every inch truly matters. This is the magic of technology. Turbofan engines that power sky giants like Boeing and Airbus planes might seem like something straight out of a sci-fi movie, but they're the pinnacle of engineering genius. So how do you take tens of thousands of parts and ingredients, almost like puzzle pieces, and turn them into these incredible machines? Ordinary metals simply won't cut it. These engines have to function in conditions where temperatures soar above 1,800 degrees Fahrenheit. That's hellishly hot, and regular steel just can't take it. Enter titanium alloys, lightweight, incredibly strong, and heat-resistant. For the hottest parts of the engine, nickel-based superalloys are used. And trust me, these are no ordinary metals. They're 21st century alchemy. Carbon fiber composites, by the way, are used in the fan blades to reduce weight while maintaining strength. This extreme heat is generated during the combustion process in the engine's combustion chamber, arguably one of the most critical components of a turbofan engine. Here's how it works. Aviation fuel, typically jet fuel, mixes with air and ignites, producing superheated gases. These gases accelerate to insane speeds and temperatures, often exceeding 1,800 degrees Fahrenheit, sometimes even reaching 2,700 degrees in modern engines. This heat is vital for achieving maximum thrust efficiency. The hotter and faster the gases, the more energy they produce to drive the turbine and propel the aircraft forward. Here lies the ultimate challenge. The engine not only needs to endure these extreme conditions, but also perform flawlessly, without a single hiccup. That's why cutting-edge materials like titanium alloys and specialized composites are a must. They can withstand both extreme heat and intense mechanical stress. You know what's truly mind-blowing about making these engines? Even individual components like turbine blades are crafted with micrometer precision. For example, blades are cast in a vacuum to ensure they're free of even the tiniest cracks. Some blades are designed with a single crystal structure, meaning the metal has zero seams. But wait, there's more. 3D printing? Yup, it's used too, especially for intricate parts that traditional casting just can't handle. Turbine blades are the heart of the engine. They operate in the hottest zone, converting the energy from the hot gases into rotational movement. First, a wax model of the blade is created. It's almost like artistic sculpting. Only here, precision down to micrometers is crucial. This wax model is then dipped into a special ceramic solution, which hardens into a strong mold. The wax inside is melted away, leaving a perfect cast for the blade. The ceramic mold is now ready for the most critical stage. Now comes the real show. Superalloys, made of nickel, chromium, and other heat-resistant metals, are melted in a special furnace to temperatures exceeding 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But here's the catch. It's not just about the material, it's about how it's done. To ensure the blade can handle enormous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams, micro cracks, or grains like regular metals do. Why is this important? In these conditions, seams or cracks are like a ticking time bomb. One small flaw, and the blade fails. Single crystals are grown through a slow cooling process. The mold filled with molten metal is gradually lowered into the cooling zone of the furnace. This process can take days, but the result? A blade that's incredibly strong and durable. Once the metal cools, the ceramic mold is broken away, and the blade undergoes meticulous polishing. A special heat-resistant coating may be applied to help it withstand extreme temperatures even longer. And yes, each blade is inspected individually. Even the slightest defect means it won't make the cut. Fuel nozzles, combustion chamber parts, or even compressor blades in aviation are often made using 3D printing. For instance, GE Aviation prints fuel nozzles for its engines that are 25% lighter, but 5 times stronger than traditional ones. Layer by layer, using powder and light, components are created that make planes fly faster, farther, and more efficiently. First, engineers create a digital 3D model of the part with maximum precision. Every curve and cavity matters. Why? Because these components often operate in environments where even a millimeter can make all the difference, from engine efficiency to reliability. This digital model becomes a map for the 3D printer, which knows exactly where and how to build the required shape. Instead of a solid chunk of metal, ultra-fine powder, made from titanium, nickel, or Inconel, a super strong aluminum alloy, is used. It looks like sand, but the particles are so tiny they're almost invisible to the naked eye. The powder is loaded into a special reservoir, becoming the building material. The printer's working principle is simple yet genius. It melts the powder using a laser or an electron beam. The laser heats the powder to a temperature where it literally fuses into a solid metal structure. Then, another layer of powder is added, and the process repeats. This method is called selective laser sintering or melting. And here's the cool part. 3D printing can create even the most complex geometric shapes. For example, components with internal cooling channels that simply can't be made using traditional casting or milling. In conventional manufacturing, you often start with a big piece of metal and carve away the excess. It's not only time-consuming, but also expensive because so much material gets wasted. 3D printing flips the script. you only create what's needed, with zero waste. But the part isn't ready yet. After printing, it undergoes heat treatment, heating, and gradually cooling to relieve internal stresses in the metal. Then comes final grinding, polishing, or machining to fine-tune precision. And of course, every part undergoes rigorous testing. Because here's the thing, if a part fails under pressure, the consequences could be catastrophic. Engine assembly takes place in a massive hangar, where every inch of space is filled with tools, engine parts, and technicians in overalls, all focused on creating something extraordinary. This is the final stage of building an aircraft engine. Here, individual components, like blades, compressors, combustion chambers, and casings, come together to form a single unit capable of lifting an airplane into the sky. It all starts with the engine casing, a giant metal cylinder that serves as the skeleton, where everything else is attached. The casing is made from titanium or nickel alloys because it has to withstand insane forces. Engineers work like watchmakers. The casing is mounted on a massive rig to ensure perfect alignment. Then come the compressors, rows of blades responsible for compressing air before it enters the combustion chamber. Each blade is installed one by one, almost like decorating a giant wheel. Every single blade is manually inspected because even the tiniest defect could ruin the entire assembly. After the compressors, it's time for the turbines. These are the blades that convert gas energy into movement. They're installed with such precision that the gap between the blades and the casing is sometimes measured in micrometers. Next comes the combustion chamber, the engine's hell zone. This is where compressed air mixes with fuel and ignites. Engineers install special nozzles to ensure fuel is delivered evenly, and everything here has to be flawless. A nozzle at the wrong angle could reduce efficiency or even cause engine failure. Running through the entire engine is a central shaft, essentially the backbone. At one end of the shaft is a fan, a massive wheel at the front of the engine, and at the other end is the turbine. When the turbine spins from the force of hot gases, the shaft transfers this energy to the fan, which draws in air. Installing the shaft requires specialized robots. This part of the process demands surgical precision, as even the slightest misalignment can cause vibrations that could kill the engine. Once the engine's internal components are assembled, external systems are added. Fuel lines deliver jet fuel to the combustion chamber. The oil system ensures all moving parts are lubricated. And the electronics? The engine is packed with sensors that monitor temperature, pressure, RPMs, and much more. These systems are attached using cables, tubes, and bolts that must withstand both vibration and extreme temperatures. After assembly, the engine isn't immediately installed on a plane. First, it's mounted on a test stand that simulates real flight conditions, from takeoff to turbulence at altitudes close to 33,000 feet. This is the most spectacular stage. Running the engine at full power fills the air with a deafening roar, audible from miles away, and streams of blazing exhaust gases. The engine is pushed to its limits for hours as engineers test its strength, durability, and efficiency. Once the engine passes all tests, it's disassembled. Key components are rechecked, and then it's reassembled for final delivery. The finished engine is packed and shipped to Boeing or Airbus, where it becomes part of a new aircraft. Piece by piece, engineers craft the heart of an airplane, a marvel capable of carrying thousands of passengers across continents. Isn't this a modern masterpiece? Let us know if you'd like to see more videos like this. What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, there can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds, that's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. Robotic arms, lasers, and 3D printers, creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part, final assembly. Rockets are assembled step by step, the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions: vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings, but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. One factory, 1 million chickens, over 500,000 eggs every single day, and roughly 120 tons of feed. Imagine that. Automated systems handle feeding, sorting, and packaging to keep this process running non-stop. Every day, these chickens drink enough water to fill 29 Olympic-sized swimming pools. Modern tech makes it possible for a chicken metropolis to run with just about 100 workers. How is that even possible? You'll find out in our video. Chickens on large farms are kept either in cages or in free-range systems. If they're in cages, these are arranged in multi-level rows. Think of it like a chicken skyscraper. Each cage has everything a chicken needs: perches, feeders, drinkers, and even a sloped floor so eggs roll straight into a collection tray after being laid. On the other hand, free-range chickens have more space to roam. They get access to the outdoors, though it's usually not a lush green field, but specially designed enclosed areas. Even in these systems, everything is organized down to the smallest detail. This factory houses 1 million chickens in a caged system, covering over 25 acres. By comparison, the same number of birds in a free-range system would need more than 80 acres. Here's another fascinating fact. Modern farms maximize vertical space, especially in caged systems, to optimize efficiency. Most of the area is used for multi-level production facilities, housing cages, feed silos, sorting rooms, and staff areas. The chickens are fed specially formulated feed to ensure consistent egg production. This feed is a mix of grains, corn, soybeans, and added vitamins and minerals. And here's the kicker. Every single gram of feed is crucial because it determines the quality and quantity of the eggs. Feed is constantly tested for protein, calcium, and potential contaminants. Some farms even add herbal extracts to keep the chickens healthy without antibiotics. Large farms use automated feeding systems. Feed is distributed through pipes or conveyor belts, filling feeders in the cages or barns. Sensors monitor feed levels and automatically dispense more when needed. Chickens receive feed tailored to their stage of life. Young chicks get starter feed rich in protein and energy. Layers receive feed high in calcium, vitamins, and trace minerals for strong eggshells. Chickens nearing the end of their life cycle get finisher feed. The feed also includes additives to support digestive health, boost immunity, and improve egg quality. Chickens are fed 2 to 4 times daily, depending on the system. Some farms schedule feedings right before laying time to encourage consistent egg production. Layers consume about 5 ounces of feed daily. For 1 million chickens, that's nearly 120 tons of feed every day, or about 40,000 tons annually. Just look at the massive silos and transportation systems needed to manage that volume. In addition to feed, chickens are provided with clean drinking water. Nipple drinkers allow them to drink without spilling. 1 million chickens require over 2.5 million gallons of water annually, roughly the amount held by 29 Olympic-sized swimming pools. Feed is stored in silos, protected from moisture and mold. Its nutritional content is constantly analyzed to ensure quality. Modern farms even use software to track how much feed each group of chickens consumes. In some free-range systems, chickens are also allowed to forage for grass, insects, and grains, making their diet more natural. But even here, the primary feed is delivered automatically. Feeding systems are key to ensuring chickens lay eggs consistently and stay healthy throughout their production cycle. After laying, eggs roll into trays through special chutes. From there, they're transported on conveyor belts. Imagine an endless line of eggs floating towards sorting machines. These machines check for defects, discarding damaged or undersized eggs using special scanners that literally illuminate the eggs. It's futuristic. Before packaging, eggs are carefully washed in warm water with gentle disinfectants. This step ensures their safety. And no, it's not just a quick rinse. Eggs go through several warm water baths to remove dirt and microorganisms. Then they're dried and coated with a thin layer of food-grade wax for protection. At the sorting stage, each egg is weighed and categorized: large, medium, and so on. Depending on the category, eggs are packed into boxes. Simultaneously, shells are dried to prevent moisture that could lead to bacterial growth. Clean inspected eggs are placed in cartons or plastic trays by automated arms. Packaging includes details like packing date, grade, size, and producer certification. Storing such a daily volume of eggs requires refrigerators with over 70,000 cubic feet of capacity, about 40 large refrigerated trucks. After packaging, eggs are sent to storage facilities or logistics centers. Here, strict temperature controls between 32 and 40 degrees Fahrenheit keep them fresh. Eggs are transported in refrigerated trucks to prevent spoilage. At distribution centers, eggs are sorted based on supermarket orders and quickly delivered to stores or markets. Modern logistics systems reduce the time from farm to shelf to just a few days. Once on supermarket shelves, eggs are stored in refrigerators to maintain freshness. Consistent storage temperatures are crucial because sudden changes can cause condensation, increasing the risk of shell contamination. Consumers choose eggs based on size, price, brand, or labels like organic or free range. At home, eggs are stored in the fridge. Freshness is easy to check. If an egg sinks in water, it's good to use. Although large-scale farms are resource-intensive, many are adopting eco-friendly initiatives. These efforts not only reduce environmental impact, but also meet growing consumer demand for sustainable products. Some farms invest in solar panels on facility roofs or nearby solar fields, covering 30 to 50% of their energy needs. Chicken manure, a natural byproduct of any farm, is a valuable resource for agriculture. Chickens produce as much manure as the feed they consume, over 100 tons daily. Manure is collected, dried, and processed into organic fertilizer. Instead of creating waste, farms provide a product that restores soil fertility and reduces reliance on chemical fertilizers. Fertilizer production from chicken manure also lowers methane emissions compared to natural decomposition. Did you know a single chicken lays 1 egg a day? Of course, 1 million chickens don't equal 1 million eggs daily, since some aren't laying yet or have stopped laying. Still, production numbers are impressive, over 500,000 eggs each day. Stack those eggs, and you'd get a column over 29,500 feet tall, 23 times higher than the orbit of the International Space Station. Younger chickens lay eggs almost daily, while older ones do so less frequently. Balanced feed helps boost egg production. Factors like temperature, lighting, and stress-free conditions also play a big role. During winter, shorter daylight hours can slightly reduce laying rates. American eggs are rich in protein, vitamins D and B12, iron, and other nutrients. There are even eggs with higher omega-3 content, depending on the chicken's diet. You know what surprised me the most? The small workforce. Modern automation allows a 1 million chicken farm to operate with just 100 or so workers. Their tasks include equipment monitoring, veterinary care, and managing feed and egg logistics. A farm of this size can generate up to $50 million in annual revenue. This makes a significant contribution to the local economy, especially in logistics, feed production, and processing. These numbers show just how massive and coordinated the effort is to keep a steady flow of eggs heading to stores and ultimately to our kitchens.